All right, we're back to talk about antimatter, which is an interesting topic in that it sounds like it's made up, but it's totally real, and it has some very interesting applications. About 100 years ago, 1920s, 1930s, a new type of matter was proposed and then discovered, and I'm going to oversimplify things here, but to give you an analogy, if I were to ask you what the square root of 4 is, and you were to tell me it's just 2, you would only be half right. Because as you probably know, the square root of 4 is equal to either positive or negative 2. Depends on whether we want to know the positive, whether we want to take the positive or the negative. Both of those, both positive 2 and negative 2, if you square them, will give you 4. So, antimatter was discovered kind of along the same lines. There ended up being, I think, from what I understand, a square root in the equation, and the guy who first proposed antimatter said, well, wait a sec, if this equation predicts the existence of an electron, then couldn't I also use this equation to predict the existence of basically something that's like an electron, but is the exact opposite sign? And it turns out that you can. Antimatter consists of particles that have the same mass as the normal versions of particles, but they have the opposite electric charge. So, for example, the first particle of this type had a mass that was the same as an electron's mass. So 9.11 times 10 to the negative 31st kilograms had the same mass, but instead of having a negative charge, it was actually positively charged. It had the same amount of positive charge. It was plus 1 elementary charges, 1.6 times 10 to the negative 19th C. So it looks exactly like an electron, but it has a positive charge. And this was first predicted, and no one had ever seen one before, but then we went and ran some experiments, and it turns out that these particles did in fact exist. We found evidence, we did experiments to find out that this sort of thing actually does happen. And the particle was called a positron, kind of like you take the words positive and electron, and you kind of push them together, you get a positron. And a positron is the first example of what is known as antimatter. You can also call a positron like an anti-electron, but positron is just a snappier name. So antimatter, every particle of normal matter has an antimatter counterpart. And the way we show that is to draw a line over the top of that particle's symbol. So for example, a positron is denoted by realizing that a positron is just an antimatter electron. An electron is symbolized by E, and we draw a line over the top of it. So that means the antimatter version of the electron, which is the positron. So the defining characteristic of antimatter is that it is the opposite charge. It's a particle with the same mass and same other properties, but the opposite electric charge. So you can have an antiproton. Instead of being positive, it would be negative, but it would have the same mass. Even a neutron has an antiparticle. Now you might say, wait, how do you have the opposite charge of 0? Their antiparticles are still neutral, but they have other differences. Antimatter isn't just the electric charge is different. There are some other things that are different, but those are more advanced. We don't have to talk about those. They're different in other more complicated ways. Probably one of the more interesting things that happens with antimatter is called annihilation. If you have a matter particle and it interacts with its antimatter counterpart, the two particles will annihilate each other. And basically what this means is they destroy each other. Both particles will have their masses turned directly into energy. And we've already looked at the relationship between mass and energy. Remember, we talked about E equals mc squared. So, if you have two particles that are annihilating each other, you take the total mass that's getting annihilated, so the mass of the two particles, essentially, you have to account for both of them, multiply it by c squared, and that's how much energy comes out. The only thing is this only happens if particles meet their direct counterpart. So for instance, an electron and a positron, a proton and an antiproton, a down quark and an anti-down quark. It does not happen, for example, if a top quark meets an anti-down quark. It's not just any two pieces of matter and antimatter come together. It has to be the exact antiparticle. And as a matter of fact, we actually have particles called mesons, which are made up of quarks and antiquarks. Obviously not the same antiquark, but quarks and antiquarks nonetheless. these particles are typically lighter than baryons. To get a meson, again, you take a normal quark and an antiquark. So one example, and again, it's a very short-lived particle. They don't stick around too long. They do decay very quickly. Mesons do in general. One particle, one meson, is known as a pion. This particle is composed of an up quark and an anti-down quark. Again, those won't annihilate because it's not the exact same. It's not the exact opposite particle. What will the charge of this be? Well, an up quark is positive 2/3 E. Oh, and by the way, the symbol for this would be U and then a D with a line over it. Up, anti-down. So we have positive 2/3 E. A down quark is normally negative 1/3 E, but since it's an anti-down quark, it's going to be positive 1/3 E. So that equals positive 1 E. So a pion has a charge of positive 1. Again, this is a particle that must be allowed to form because the overall charge is now a whole number. Okay? So mesons are a little weird. They combine antimatter. They are real. We have observed them. They don't last very long, but it does show that antimatter is a real thing. Now, for our last category, we have hadrons. And if you look at the chart, hadrons are just anything that are made up of quarks, okay? Hadrons can be split into baryons and mesons, and baryons and mesons are just particles made up of quarks. So a hadron is anything made up of a quark, okay? Hadrons. They're both made up of quarks. Hadrons are simply particles that are made up of quarks and are affected by all four fundamental forces, including the strong nuclear force. So remember that this differentiates them from leptons because leptons are not found within the nucleus, therefore they do not interact via the strong nuclear force. And with that, we have officially come to the end of the physics curriculum. You've officially made it. You've done everything. There's one last thing that I always show my classes, though. And I'll probably, if we do have class, I'd probably play this in class too, just so you get an extra chance to laugh at it. You know what? No, we'll have to play it in class. In any case, we're officially done with the curriculum. It's been a great time making these videos. It's been a great time working with you guys. I hope you've enjoyed your study of physics, and I hope you, I'd love if you went on and studied more physics, either with me in AP Physics 1 or maybe in college. If you don't, I hope you learned something about physics or something about hard work and perseverance that you can take with you in the rest of your life. So thanks for sticking with me. Good luck, and it's been a pleasure. I'll see you later.